Okay, I just basically cobbled together a Class C amplifier circuit. I know I covered that in a different video, but this one has a resonant tank attached to it, so that basically the Class C amplifier is acting like a tickler. And this is how it's typically used, this kind of amplifier, by the way. I decided to go ahead and add a series impedance to it just for shits and giggles. It works either way. It's, you know, in fact, I'll show you that in a minute. I just was like, well, I wondered what would happen because, I kind of worry that this is being dropped. This signal source is being dropped across a diode, and there's no kind of feedback mechanism limiting that source except for the diode itself. And yeah, you got this resistor here, but that's really just siphoning away current from the transistor. So, I just thought I'd stick that in there for the hell of it, you know, just to see what the effect was, and to actually buffer your, analog discovery just in case. It's not supposed to generate more than too much current though, even without that. So it's no big deal. But that's why I have this in here anyway. So, but you can use it without this. But yeah, I've got it set for, for values that put its resonant frequency around roughly 2.3 kilohertz. So it's not RF by any means, and that means I can look at it with analog discovery a lot easier. So, you can see the kind of frequency I'm throwing at it right around there. And that's the resulting waveform. The blue is my applied signal, but that's before the resistor. So you can see where the scope probe is versus the red signal lead. So going into the amplifier. And oh, this is a hell of a lot better of a breadboard than the one I've been using, by the way. Yeah, that really sucks. That other one really sucks. But I have it, set aside with that two-stage feedback amplifier from before. And oh, by the way, I did run an extra analysis on this before I took the thing, disconnected it. In this, I set the gain to maximum, so you can see it's about 100, down at low frequencies, but then it falls off, um, to about 70, at about 4 kilohertz. Then it remains pretty steady up until about 1 megahertz and then starts falling off, which is what I'd expect for a higher gain amplifier, because they still are subject to gain bandwidth products. So the higher the gain you set it, the less bandwidth you're going to end up getting, and that's how it works, not just with op-amps, but most amplifiers. So, but at any rate, but yeah, we're not producing a very good sine wave here. But then again, I mean, I'm using one of those little tubular inductors because I had them, in a kit I bought from Amazon for pretty cheap, $11. It has an assortment of them. So that's handy because instead of digging through my inductor junk boxes down there, I'm trying to do with an LCR meter, trying to find one suitable, and then not being able to plug it into breadboard because I got a bunch of solder on it. So at any rate, it's just interesting seeing here, and like I said, the blue is my input signal, and I got that set to, because I'm pumping at 1.65 volts peak into it, so it's like a 3 volts peak to peak, which on the simulator over there, I'm putting 2 volts into it, as you can see on the graph, plus or minus 2 volts and 2 volts peak. But it's supposed to give a higher output. It's giving plus or minus 12 volt, on the simulator. But we're not getting that, especially going through that input impedance. In fact, let me go ahead and I'll move our signal from there to there, and now it's direct, just like you see there. And the signal output is now 9 volts as opposed to like the 6 or so that we had, but still it's certainly not a sine wave, but this is about the best balance point, symmetrically speaking, you can get, and it's about right there. So, and funny thing is, at certain frequencies you can certainly hear this thing, it's audible, just barely, but audible. And I can even take this up to you know, 2 volts or so, and it kind of decays back down to a certain level, but there's no real gain from it. In fact, it's diminished, if anything. I'll take it back down to where I had it. No reason to overload the analog discovery, even though I don't think it would. It's probably just, you know, a few hundred microamps. But at any rate, what's interesting here is to look at what happens, you know, again, because these are those tubular inductors, so as a result, they're going to be very low Q. They're going to have really high, you know, series resistance, you know, winding resistance. So, you know, it's to be expected that you're not going to get excellent results out of this thing. That would make a, you know, a broad range. In fact, I can tune it, you know, and adjust it. We're at 2.6 kilohertz right now, but I can, you know, adjust it down, you know, and you can see what happens to the waveform. I mean, and what you're seeing here is rather interesting, because this little peak here is actually the classic little LC oscillator die-off you see here, but it's so heavily damped because of that coil that it dies off extremely fast. So, you know, but as a result, you know, we're not tickling it fast enough, basically, but it's still oscillating, but it dies off just super quick. And again, that shows you that this is probably not a good coil to actually use with this circuit. But, you know, and the best you can do, you know, was where I had it before. You know, as I up the frequency, you know, you can see that it doesn't have time to die off anymore. In fact, right here, I can hear it. I don't think you can hear it, because I think I don't think I got the camera mic active. I think I'm using this mic here. But yeah, you can actually hear a high-pitched whine from it. So, but again, you know, that's about, you know, where it should be, you know, so it's just interesting. And it's interesting too that, you know, the actual voltage input to the transistor is just a little above a diode drop, right? You know, because that's, you know, as you can see over here, you know, that's basically all you got, you know, and not staying in the way is a diode voltage drop. So the voltage itself isn't going to be very high, but, you know, it's still tickling that coil, and the coil is oscillating, you know, with the energy stored in it, you know, at a much higher voltage. So you can see about 10 volts, you know, is what we're getting out of it. So, but at any rate, this is a low frequency wave experimenting around with what's traditionally a circuit used for RF purposes. So, but it just shows, you know, you don't actually have to mess with it at RF. So that's kind of one of the points of the video, you know, is that, yeah, it worked. And so even though, you know, Volstat, you know, is based on a more ideal inductor, you know, as you can see, and, you know, this is anything but ideal. So anyway, cheers.